Welcome back, everyone. We just finished up question number 2, so let's take a look at question number 3 on the 2005 Grade 9 contest, the Friar contest. Alright, so it's got a special kind of triangle. A Nakamoto triangle is a right-angled triangle with integer side lengths, which are in the ratio 3 to 4 to 5. Okay, 3, 4, 5, very common right-angle triangle. So for example, a triangle with side lengths 9, 12, and 15, well, that's in the ratio of 3, 4, 5, because that's 3 times 3, 4 times 3, 5 times 3. That's a Nakamoto triangle. Alright. A part. If one of the sides of a Nakamoto triangle has length 28, what are the lengths of the other two sides? So the way that's phrased, that suggests to me that there's going to only be one triangle, and one Nakamoto triangle who has a length of 28 as the side. Okay. Remembering we have integer side lengths, so this needs to be 3 times something, 4 times something, or 5 times something. So we can take a look. Right, we're going to have to be able to find some integer k so that 28 is either 3k, 4k, or 5k. Now the reason it has to be an integer, it can't be some sort of fraction, is because 3, 4, and 5, they have a greatest common denominator of 1. And so that would produce some fractional length on another integer side. Okay, and we could write that up if we were aware of that and we were feeling a little nervous, but it's the 9th grade contest. They're not really looking for the in-depth discussion as to why you can't have fractions here and greatest common divisors. This is meant to be sort of an introductory question. A parts are usually very simple. We'll get into the hard stuff in a little bit. So we can immediately notice that 3 does not divide 28, and 5 does not divide 28. Make that line a little thicker. Does not divide. So then we know 28 is going to be the side associated to 4 in the ratio 3, 4, 5. And at that point, we can see k is equal to 7. Just divide 28 by 4, you'll get 7. So 4 times 7, that's going to be 28. So if this is the 4k one, then the other lengths are going to have to be 3k and 5k, which we quickly see are 21 and 35. And that's sort of our final little statement, not a whole lot there. What we can do is we can double check that these guys at least satisfy Pythagoras' theorem. That way we haven't made some sort of error anywhere. So 21 squared plus 28 squared, that's 1225, which many of you out there will know is 35 squared. Or you can just hit the square root button on the calculator. That really does it for part A. Again, if you're worried about just saying that some integer k here, if you're worried about that, you are likely smart enough that you will probably know, just simple argument. Assume that k was a fraction, and use a greatest common denominator or greatest common divisor argument to show that one of the other ones, 4k, 5k, 3k, one of them will have to also be a fraction. But again, don't really worry about it. Okay. So we got the lengths of the other two sides. This one is at best a 2 marker, worth 2 marks, and I think all these are out of 10 usually. So there's 2 marks, and then you could have 4 marks and 4 marks, or 3 marks and 5 marks. It's sometimes on contests it is useful to try and think, okay, what mark, how many marks is a part worth? Because that really, you don't want to go overboard on justification. It's kind of a very important thing. You don't want to spend so much time rigorously writing up A part that you run out of time to do C part, or you run out of room to do C part. So it's always a good idea to maybe guess, okay, this is probably the answer. What are the highlights? What are the really difficult parts? Each one of them is probably worth a mark. And so that really tells me that a part is probably worth 2 marks. One for realizing 28 would be 4k, and the second mark for the answers. Now it might be 3 marks. One for realizing 28 is 4k, and then one for the 21 and one for the 35 at the end. But no more than 3 marks at worst. And so that really tells me that B is probably 3 marks, maybe 4, and C is 4 marks, maybe 5. Usually they increase in difficulty, the questions, and so the increase in marks, because the more difficult a question, the more you'll have to do to get an answer, the more you'll have to do to justify your answer, and so there's more room for marks. More room for errors means more marks usually. So that's just sort of a public service announcement about not being too rigorous on questions that are likely worth very little. Okay, back to the question B part. Find the lengths of the sides of the Nakamoto triangle, which has perimeter 96. Explain how you got your answer. Okay. So, what's perimeter again? Well, perimeter is the sum of the side lengths of the triangle. So, where are we? We have 5k is the hypotenuse, 4k, and 3k, those are the sides. Or the legs, I believe is what they're called. So we have a single variable k, that's what we want to solve for. And what didn't you know it? Knowing what the perimeter is gives us a single formula that we can solve for k. So knowing that it's 96, well, that's just the sum of the side lengths. So that's 3k plus 4k plus 5k. We don't need to know what k is yet. We're going to figure that out. So adding all those up, 3 plus 4 plus 5, that's 12. So we have 12k. K is going to be 96 divided by 12, and you can either get your calculator out or you can just know that that's going to be 8. Either or. And we're asked for all the side lengths, right? Find the lengths of the sides. Okay. We get 3 times k is 24. 4k, so that's 4 times 8. That's 32. And 5k, that's going to be 40. And if we wanted to, we could put little boxes around them. We could have put boxes around the 21 and the 35 in the previous question. It just helps people who are marking. You box important information, that way they can easily find it. And if we wanted to, we could. We don't have to. If we're worried about time, we want to get to question number 4, we don't have to, but we could quickly add these up and realize that the sum is 96. So our perimeter is safe. It is the correct answer. All right. So C part. Determine the area of each, so I'm guessing there's going to be a couple, each of the Nakamoto triangles, which has a side length of 60. Okay. So remember the side length of 28. The reason we were able to figure out exactly one triangle there is because 28 is not divisible by 3. It's not divisible by 4. It's not divisible by 5. It's only divisible by 4. So it can only be the length associated to 4 in the ratio 3, 4, 5. But 60 is divisible by 3. 60 is divisible by 4. 60 is divisible by 5. Okay? So really, it could be any one of them. It could be the 3, it could be the 4, or it could be the hypotenuse, which is associated to 5. So we're likely going to get 3 different triangles. So we want the area of each of the Nakamoto triangles. So 3 divided 60, 4 divided 60. So let's suppose that 60 was 3k, so it's the 3 in our ratio. Well, then k is going to be 20. So I'm guessing for C part, it might even be worth 3 marks. 1 for each of the areas of the triangle. Maybe an extra mark for realizing that 60 can be in 3 different spots. So we get 4k. It's going to be 80, and 5k. It's going to be 100, and we want the area. One half base times height. So 1/2 3k times 4k. Right, because it's a right angle triangle, so we get base and we get height. Which is going to be 6k squared. So really, we don't even need to figure out these other side lengths. So 6 times 400, that's going to be 2400. Okay. Okay, so that's one of them. If we take a look at another one, if 60 is the 4 side, the side associated to 4 in our 3, 4, 5 triangle, we get k is equal to 15. We don't need to get the other sides, but we could work them out. 45 and 75. The area we know is going to be equal to 6k squared. So that's 6 times 15 squared, which is 225. That's 1350. Okay. So the last case, if 60 was 5k, if it's the hypotenuse now, then k is 60 over 5, which is going to be 12. A smaller k value means the area is going to be smaller. So what's that? That's 6 times 12 squared. Or really that's just 4 times 216, which is 6 cubed. But we get our answer of 864. And we just double check what the question was asking for. Determine the area of each of the Nakamoto triangles, which has side length of 60. Explain how you got your answers. Well, I think we've done a pretty good job of that. We explained that 60 could be in each of the 3 possible locations. And we explained how to get the area. We even figured out the side lengths. Here and here, the other sides. But really, it's this formula right here that does it. Area is 1/2 base times height. Six k squared. I'm going to write these guys in increasing order. 684. Oops, no comma there. There's a comma before it. 1350. And finally, 2400. 2400. All right. It's a nice little right angle triangle question. The Pythagoras theorem didn't really come into it a whole lot. That's actually pretty nice. Right angle triangle, we never had to really use Pythagoras' theorem. It was really just a bunch of sort of triangle ratios for the most part. So a nice little question. And we're almost done the contest. We're almost done the 2005 Friar. And yeah, I got nothing left to say. Join me in the next video if you'd like for the last question, question number 4.